So this is a video about rational functions. As you see right here, the rational functions is the topic for today. So first of all, you see the definition here. A rational function, f of x, is basically a function where you have a fraction, and at the top you will have a polynomial of some sort, and at the bottom you also have a polynomial of some sort. And it looks very complicated, but it's just a definition. So I have a few examples here. There is a function f of x, g of x, and h of x. As you see, all of them are fractions. You have some sort of polynomial, this quadratic trinomial here at the top, and this quadratic trinomial at the bottom. So if you were to compare this function f with the definition, you would say that a, for example, a here is 1 because that's the number next to your x squared at the top, and then z right here, this z here is also 1. That's a number in front of x squared at the bottom. Now also, if I ask you what is n, this n right here, which is the highest exponent at the top, you would say it's 2. And so is m. This m is also 2. Continue. Let's look at this function g here. Again, if you compare the function g with the definition right here, you will learn, or you will notice that your a here is, which is the number in front of the highest power of x at the top, is 1, and so is z. Z is the number here in front of the highest power of x at the bottom. And then your n is 1. That's the power of x at the top, the highest power of x at the top, and your m, which is the highest power of x at the bottom, is 2. So we're going to start by determining domain of these three rational functions. And right here it says factor the denominator first, and that's precisely what we're going to do. And we're going to find a domain, and we'll write it in interval notation for each one of these three fractions. So we're going to first do what we told, which is factor the denominators. So I'm going to look at the denominators only. Numerators do not participate in finding the domain, only the denominators. So we're going to factor this first trinomial at the bottom. It's a quadratic trinomial. I'm looking for two numbers that multiply to 30, but also add to 11. Those numbers are 5 and 6. 5 times 6 is 30, and 5 plus 6 is 11. So this denominator here for function f factors into x plus 5 and x plus 6. Now let's factor x squared minus 25. This is the difference of squares. X squared here is x times x, and 25 is 5 times 5. So this will factor into x minus 5 and x plus 5. And then this last denominator is the binomial of first degree, and it's not factorable. So I'm just going to rewrite it as is without factoring it because you can't. Okay. So to find the domain, we're going to factor the denominators, which we did, and then we're going to set them equal to 0 and solve those equations for x. So we're going to set this one equal to 0, and then we're going to set this one equal to 0, and also this one here equal to 0, and solve each one for x. Well, to solve this first one for x, what we need to do is take each factor separately, x plus 5 and then x plus 6, and set each of them equal to 0. So I'm going to say x plus 5 equals 0, which means our x is equal to negative 5, because to solve it, you just take plus 5 and make it negative here. And then the x plus 6 equals to 0, which means x is negative 6. Okay, now we're going to do the same for this second function, the g of x. We have it in factored form, x minus 5, x plus 5. Very similarly, I'm going to say x minus 5 equals 0, which means x is equal to 5. And then I will also do the same for x plus 5. So once my cursor gets here, so x plus 5 is equal to 0, which means x is equal to negative 5. Okay, now for this one here, you basically only have one factor. You don't have the other set of parentheses, so you just are going to have one answer here, x equals positive 1. So x equals positive 1. So how will these numbers that we obtained by factoring denominators and solving that equation, denominator equals to 0, how will these numbers help us to state the domain in interval notation? Well, the domain of a rational function is always from negative infinity to infinity with breaks at these numbers. So that's what we need to show. We need to show that the domain goes all the way from negative infinity to infinity with a break at -6 and then a break at -5. I'm saying -6 first because it comes first on x-axis or a number line. So we're gonna write this. We start at negative infinity. I'm just gonna use 2 zeros for infinity. Then we have a break at -6, so we exclude -6 by giving it this parenthesis. Okay, then we're going to pick up again at -6 all the way until -5, again excluding the -5, giving it a parenthesis, finally picking up again at -5 and going all the way to positive infinity, and there's your domain for function f. So basically it says you go all the way from negative infinity to infinity with a break at -6 and the break at -5. So very similarly, I'm going to say this g, function g, also has the domain that starts at negative infinity and goes all the way to positive infinity with 2 breaks, one at -5 and one at +5. -5 will come first because it's the first on the number line. So from -5 to 5, and finally from 5 to positive infinity. And that's the domain of our function g. So finally, this last function here, h of x, only has one break. It's at +1. Again, you start at negative infinity, you go to 1, and then you pick up again at 1, you exclude the 1, but pick up right after you pass it and go all the way to positive infinity, and there is the domain of function h. Okay, so now we're going to move into item 2, this Roman numeral 2, which is asymptotes of rational functions. There are 3 kinds of asymptotes the rational function may have. The first one, under the letter A here, is called the vertical asymptote. Then there is this B, which is the horizontal asymptote, and there is C, which is called oblique, or sometimes it's referred to as slant asymptote. And we're going to continue working on our same 3 functions, function f, g, and h, and we're going to start by finding let me erase this here. And we're going to start by finding the vertical asymptote. So we are under the letter A here. It does give you this direction here, which is simplify the fraction first, and that's very important. We're going to do that for all 3 functions. We need to simplify those fractions if possible. If you don't, you're going to end up with extra asymptotes that aren't asymptotes, basically, for the vertical asymptotes. So to find the vertical asymptote, you need to solve the equation denominator equals to 0 and the resulting x's are your vertical asymptotes. But we must simplify the fraction first. So basically, we're going to be doing the same exact work we did for domain over these rational functions, but you have to just simplify the fraction. For domain, you don't need to. You shouldn't. All right, so to simplify this fraction, the function f, I'm going to first copy it to make it easier for me to type the fraction. And here it is, my f of x equals this. So to simplify it, let me make this a little lower here, the horizontal asymptote. I don't need those just yet. Okay, so this function f of x, and I'm going to simplify it. To simplify this fraction, I need to factor it. I already know how denominator factors. I did it for the domain. It was x plus 5 and x plus 6. Now for the numerator, I also need to factor it. So here for this quadratic trinomial, I need to find 2 numbers that multiply to 7 and at the same time add to 8. So 2 numbers that multiply to 7 are 7 and 1, and they also add to 8. 7 plus 1 is 8. So this top here will become an x plus 1 and x plus 7. All right. So the question is, can I simplify this fraction? The answer is no, because I do not have anything that matches at the top and at the bottom. They're all different, so I have to leave the fraction as is. But to find the asymptotes, I have to say denominator equals to 0, and then the resulting x's are the vertical asymptotes. I already did this work here for the domain. So I already know that when you set the denominator equal to 0, your asymptotes will be x equals -5 and x equals -6. So for function f, my vertical asymptotes are x equals -5, and x equals -6. These are my vertical asymptotes. All right, so now I'm going to do the same with my function g. So let me copy that here and paste. All right, so the idea is, again, we need to simplify this fraction, and to simplify we need to factor. The top here is the binomial of the first degree in function g, and it's not factorable. The bottom is factorable, and we already factored it today. It's right here at the top, x minus 5x plus 5. So I'm going to replace that with my two binomials, x minus 5 and x plus 5. And you see here you have x plus 5 at the top and x plus 5 at the bottom, which means this fraction actually can be simplified. So I will go ahead and simplify it. So for the top, I will have a 1, because x plus 5 is going to be gone. It cancels with this denominator's x plus 5. And at the bottom, I will be left with x minus 5. Once you simplify your fraction, you're going to solve this equation, denominator equals to 0. So my denominator that's left is x minus 5. I'm going to say x minus 5 equals 0, which will result in x equals 5. And that is the vertical asymptote for the second function, which is function g. Okay, so now for function h, we are going to try to do the same exact work. Here's my function h. And I'm going to try to simplify it if possible. So the denominator is not factorable, as we discussed when we were finding its domain, but the numerator is a quadratic trinomial. So we need two numbers that multiply to 4 and also add to 5. Those numbers are 4 and 1. 4 times 1 is 4, and 4 plus 1 is 5. So this will become x plus 4 and x plus 1. And while it's factorable, the fraction actually can't be simplified because there is nothing at the top that matches with the denominator's x minus 1. So all we do is, again, remember we're looking for the vertical asymptotes, so we're going to need to do denominator equals to 0. So denominator is x minus 1. I'm going to set that equal to 0, which will give me x equals 1, and that is the vertical asymptote for our function h. So we're done with that. Now let's move into horizontal asymptotes. For horizontal asymptotes, there are these three rules. Depending on what your function looks like, you will have a specific horizontal asymptote, or you may not even have an asymptote. So to determine horizontal asymptotes, you need to remember what these letters mean, the N, the M, the A, and the Z, because depending on those, you will be determining what your horizontal asymptote is, and if you even have one. So I'm gonna scroll back here and remind you that an N is the power at the top, the highest power at the top, and M is the highest power at the bottom. And then A is the coefficient of that highest power, called the leading coefficient, and then Z is the coefficient at the bottom. So remember, N and M are the asymptotes, and A and Z are the coefficients. Okay, so here's the rule. If the top degree, the top exponent, is less than the bottom exponent, then the horizontal asymptote is y equals 0. If the top degree is the same as the bottom degree, then to find the horizontal asymptote, you will say y equals, and then you have to divide the top coefficient by the bottom coefficient. Finally, you will have no horizontal asymptote if the top degree is larger than the bottom degree. So that's what you look for first, is the degrees at the top and at the bottom, and then depending on them, the N and the M, you're going to determine what your asymptote is. Okay, so let's look at function f. The power at the top is 2, and the highest power at the bottom is 2, so they're the same. N is equal to M, which means to find the horizontal asymptote, I have to say y equals the leading coefficient at the top divided by the leading coefficient at the bottom. So y equals, the leading coefficient at the top is 1, the leading coefficient at the bottom is 1, so 1 divided by 1 is 1. And that's the horizontal asymptote for function f. Now we're going to move into function g. So for function g, let's compare the degrees. The degree at the top is 1, This power of x here is 1, and the power of x at the bottom is 2. So the top is actually less than the bottom. The top is less than the bottom. So that means that the horizontal asymptote will be y equals 0. Y equals 0. Okay, so finally, we're going to look at our h, which this one says, so finally we're going to look at h, where the top power is 2 and the bottom power is 1. So the top is greater than the bottom. That's this third option. And that tells us that there will be no horizontal asymptote for function h. So here it does not exist. All right. So that's it for the horizontal asymptotes for our three functions. Now let's move into oblique or slant asymptotes. Now this is very important to remember that oblique or asymptotes only exist if the top degree is larger than the bottom degree. And remember, that's the only case when horizontal asymptotes do not exist. So in other words, horizontal and oblique asymptotes are mutually exclusive. You can't have both. You have to have one or the other. If you have horizontal, you won't have oblique, and if you have oblique, you won't have horizontal. So that means that because we have horizontal asymptotes for f and g, it already says it right here, so they won't exist for, the oblique asymptotes won't exist for f and g because we had horizontal. Now for h, because we didn't have horizontal, because n was greater than m, you will have the oblique asymptote. So to find the oblique asymptote, you have to long divide the numerator by the denominator, and an equation of the asymptote will be y equals the quotient while you're ignoring the remainder. So that's the rule, and here is how you finding the oblique asymptote for this function h. All right, so here is our function h, and we need to find the oblique asymptote for it. We already said that it does not have a horizontal asymptote, which means it will have oblique asymptote because the top exponent, this little 2 right here, is larger than the bottom exponent of 1. So here's how you find the oblique asymptote for this function, for any function that has an oblique asymptote. You're going to set up this fraction as long division, like so. So you're going to have the numerator inside the box, x squared plus 5x plus 4. And then the denominator, x minus 1 outside the box. And we're going to long divide. Okay, so the steps for long division are, you're going to take the number that is the first term, I guess, inside of the box, which is x squared, and you're going to divide it by the first term that's outside the box, which is x. So I'm going to do this work on the side here, x squared divided by x, and that's x, right? Because we subtract the exponents when we divide. 2 minus 1 is x to the power of 1, which is just x. This result goes to the top of your box, and that's the first part of your quotient. So this is x. Okay, then we're going to take the same x, and we're going to multiply it by this x and this negative 1. So x times x is x squared, and x times negative 1 is negative x. Those two results will go below the box. So x squared and negative 1. So now, once we have something under our original trinomial, we're going to subtract. And it's very important to think subtraction. So we're going to do x squared minus x squared here vertically. They cancel, and they always should if you're doing it correctly. And then 5, I'm sorry, this one is 1x. And then 5x subtract negative 1x. So subtract negative 1x, which actually turns this into addition, because two negatives will give you a plus. 5x plus 1x is 6x. Once you finish subtracting, we're going to bring down the final term here, this 4, so plus 4. And we're going to repeat the steps, considering 6x plus 4 being our new inside of the box binomial. So remember, the first step we did was divided x squared by this x. So now we're going to divide this 6x by the same x. So 6x divided by x is 6. This positive 6 is the second part of your result, your quotient, and you're going to place it to the top, so plus 6 here. And then the first result, remember, was the x. And then after we placed it here, we multiplied by both of these and placed those products here. So now we're going to multiply the 6 by both of these. So 6 times x is 6x and goes here. And then 6 times -1 is -6. So now we subtract. 6x minus 6x cancel. 4 subtract -6 is actually 4 plus 6, so that's a 10. And we're done because there is nothing else to bring down. This is the remainder here at the bottom. And the quotient is at the top. This is the remainder. And this is the quotient. So the oblique asymptote for our function h is y equals the quotient. We ignore the remainder. You don't need the remainder for these purposes. So the oblique asymptote here is y equals x plus 6.